Right now, somewhere in the vast darkness of space, there might be a particle that knows exactly what you're thinking before you even think it. Scientists have discovered that when two particles become quantum entangled, they share an instantaneous connection that makes them cosmic twins, forever linked across any distance. If you touch one particle here on Earth, its partner on the far side of the galaxy will instantly react, as if they're sharing the same soul. Einstein called this impossible phenomenon spooky action at a distance, and spent the final decades of his life trying to prove the universe couldn't work this way. But what if every atom in your body has a quantum partner somewhere in the cosmos? And what if consciousness itself emerges from these mysterious connections that transcend space and time? Chapter 1. The Einstein Paradox. When genius meets mystery. In 1935, Albert Einstein found himself staring at equations that seemed to mock everything he believed about reality. The great physicist who had revolutionized our understanding of space and time was now confronted with something even stranger than his own theories of relativity. Quantum mechanics, the new science of the atomic world, was predicting something that Einstein considered absolutely impossible. It suggested that two particles could become so deeply connected that measuring one would instantly affect the other, no matter how far apart they were. This wasn't just faster than light communication, it was instantaneous action across any distance imaginable. Einstein's discomfort with this idea ran deeper than simple scientific disagreement. His entire worldview was built on the principle that the universe operated according to local laws, meaning that objects could only be influenced by things in their immediate vicinity. Nothing should be able to reach across the void of space and instantly affect something else without sending some kind of signal or force. Yet quantum mechanics was telling him that reality itself was fundamentally non-local, that particles separated by billions of miles could somehow maintain an immediate, intimate connection. The phrase spooky action at a distance wasn't meant as a compliment. Einstein used these words to express his deep skepticism about what quantum theory was claiming. To him, the idea that nature operated through mysterious invisible connections felt more like supernatural magic than serious physics. He believed that if quantum mechanics was predicting such bizarre behavior, then quantum mechanics must be missing something important about how the universe really worked. Together with his colleagues Boris Podolsky and Nathan Rosen, Einstein crafted what became known as the EPR paradox, a thought experiment designed to expose what they saw as the fundamental flaw in quantum theory. They imagined creating a pair of particles with perfectly correlated properties, then separating them by vast distances. According to quantum mechanics, measuring one particle would instantly determine the state of the other, regardless of the space between them. Einstein argued that this could only be possible if the particles already possessed definite properties before measurement, hidden from our observation, but real nonetheless. This wasn't just an academic dispute about equations and mathematics. Einstein was fighting for a vision of reality where the universe made logical sense, where cause preceded effect, and where objects had definite properties independent of observation. The quantum world seemed to be telling him that particles existed in ghostly states of possibility until the moment someone looked at them, and that this act of looking could instantly affect particles anywhere in the universe. For a man who had dedicated his life to finding elegant, rational explanations for cosmic phenomena, this felt like a betrayal of everything science represented. Einstein famously declared that God does not play dice with the universe, expressing his belief that beneath the apparent randomness of quantum mechanics lay a deeper, deterministic reality governed by hidden variables we simply hadn't discovered yet. He imagined that particles carried secret information, like invisible instruction manuals that determined how they would behave when measured. If scientists could just find these hidden variables, the spooky connections would reveal themselves to be perfectly normal, local interactions that only appeared mysterious because of our ignorance. But the implications of Einstein's position were troubling in their own way. If hidden variables existed, they would need to be incredibly sophisticated. containing precise instructions for how particles should behave under every possible measurement scenario. These variables would need to coordinate perfectly across vast distances, ensuring that entangled particles always produced correlated results. In trying to eliminate the spookiness of quantum mechanics, Einstein was proposing an even more elaborate cosmic conspiracy. The philosophical weight of this debate extended far beyond the realm of physics. If quantum mechanics was correct, it meant that reality at its most fundamental level was built on connections that transcended our everyday experience of space and time. Particles that had once interacted would remain linked forever, carrying invisible threads of correlation that could stretch across the entire observable universe. Every measurement, every observation, every conscious act of looking at the world would be participating in a cosmic web of instantaneous connections. Einstein's resistance to these ideas stemmed partly from his deep commitment to realism, the belief that the world exists independently of our observations. Quantum mechanics seemed to suggest that reality was somehow incomplete without conscious observers, that the act of measurement played a fundamental role in determining what actually happened. This struck Einstein as backwards, placing human consciousness in a privileged position that he found philosophically unacceptable. The debate also touched on the nature of scientific explanation itself. Einstein believed that a complete physical theory should be able to predict exactly what would happen in any given situation, not just provide statistical probabilities. Quantum mechanics could tell you the odds of finding a particle in any particular state, but it insisted that the universe was fundamentally probabilistic, that true randomness existed at the heart of reality. For Einstein, this felt like science giving up on its mission to fully understand and predict natural phenomena. As the 1930s progressed, the quantum pioneers like Niels Bohr and Werner Heisenberg defended their interpretation with growing confidence. They argued that Einstein's classical intuitions, while valuable for everyday objects, simply didn't apply to the microscopic realm where quantum effects dominated. The quantum world operated by different rules, and trying to force it into classical categories was like trying to understand music by analyzing the chemistry of piano strings. Yet Einstein never abandoned his search for a more complete theory that would restore logical order to the universe. He spent the last 3 decades of his life working on unified field theories, attempting to find a framework that would explain both gravity and quantum phenomena without resorting to spooky action at a distance. He believed that someday, future physicists would discover the hidden mechanics underlying quantum correlations and vindicate his faith in local realism. The tragedy of Einstein's position was that his intuitions about the strangeness of quantum mechanics were absolutely correct, even though his proposed solutions were wrong. Quantum entanglement truly is as weird and counterintuitive as it seems. The universe really does seem to operate through instantaneous connections that transcend space and time. What Einstein couldn't have anticipated was that this spookiness would become not just accepted science, but the foundation for revolutionary new technologies. Einstein's spooky action at a distance has evolved from a philosophical problem into practical reality. Modern laboratories routinely create entangled particles and use their mysterious connections for quantum computing, ultra-secure communication, and precision measurements that would be impossible with classical physics. The very phenomenon that Einstein found so troubling has become a cornerstone of 21st century technology. Perhaps most remarkably, experiments have now confirmed that Einstein's hidden variable theories cannot explain quantum correlations. The universe truly is non-local in ways that would have seemed like fantasy to classical physicists. Yet this non-locality doesn't violate the speed of light limit for information transfer, preserving the insights of Einstein's relativity while embracing the quantum strangeness he could never accept. The cosmos Einstein dedicated his life to understanding turned out to be even more mysterious and wonderful than he had imagined, filled with invisible connections that link every particle to the cosmic whole. Chapter 2: The Quantum Dance. How particles become cosmic partners. To truly understand how particles become cosmic partners, we must first journey into the heart of quantum weirdness itself, where reality operates by rules so strange that even the greatest physicists struggle to believe them. In the quantum realm, particles don't behave like tiny billiard balls with definite positions and properties. Instead, they exist in ghostly states of possibility, simultaneously embodying multiple contradictory realities until the moment someone decides to look. Imagine holding a coin that isn't just heads or tails, but both at the same time. Not sometimes heads and sometimes tails, but genuinely existing in a state where it possesses the essence of both possibilities simultaneously. This is quantum superposition, and it's not just a clever thought experiment. Every electron, every photon, every fundamental particle in the universe spends most of its existence in these impossible states of multiple realities layered on top of each other. Erwin Schrödinger, one of the architects of quantum theory, found this concept so absurd that he created his famous thought experiment about a cat to show how ridiculous quantum mechanics sounded when applied to everyday objects. He imagined a cat trapped in a sealed box with a quantum device that had a 50% chance of releasing poison. According to quantum mechanics, until someone opened the box to check, the quantum device would exist in a superposition of both triggered and untriggered states. This would mean the cat itself would be simultaneously alive and dead, existing in a ghostly overlay of life and death, until observation collapsed this superposition into a single reality. Schrödinger intended this as a criticism of quantum theory, pointing out how absurd it seemed to suggest that reality depended on observation. Yet decades of experiments have confirmed that the quantum world truly does operate this way. Particles genuinely exist in superpositions of multiple states, and the act of measurement really does force them to choose a single reality from all the possibilities they were simultaneously embodying. The mathematics of quantum superposition reveals something profound about the nature of reality itself. When physicists describe a particle in superposition, they use equations that show the particle as a combination of all possible states it could occupy, weighted by the probability of finding it in each state when measured. It's as if reality keeps a running tally of all possibilities, allowing particles to experience every potential version of themselves simultaneously until interaction with the outside world forces a choice. This quantum choreography becomes even more mysterious when particles learn to dance together. Quantum entanglement emerges when two or more particles become so intimately connected that they can no longer be described as separate entities. Even when vast distances separate them, they become parts of a single quantum system, sharing a combined reality that transcends individual identity. The birth of entangled particles often begins with a single quantum system that splits into two parts while preserving some fundamental property. Picture a particle with zero total spin that spontaneously breaks apart into two daughter particles. The laws of physics demand that the total spin remain zero. So if one daughter spins up, the other must spin down. But here's where quantum weirdness transforms simple conservation into cosmic mystery. In the classical world, we might imagine that the particles decide their spins at the moment of separation, like flipping two coins that land on opposite sides. One particle would carry away an upward spin, while the other carried a downward spin, and they would maintain these definite properties as they traveled apart. But quantum mechanics reveals a far stranger reality. According to quantum theory, neither particle actually possesses a definite spin direction after separation. Instead, each particle exists in a superposition of both up and down spin states simultaneously. The conservation law creates a correlation between the particles without determining their individual properties. The first particle exists in a ghostly state of being both up and down, while the second particle mirrors this superposition in the opposite direction. They share a combined quantum state where the possibilities for both particles are intertwined in a cosmic dance of correlated uncertainty. This entangled state represents something that has no classical analogy. The particles aren't just correlated in their properties, they share a single, unified quantum reality that encompasses both of them simultaneously. When physicists write the mathematics describing entangled particles, they discover that no equation can separately describe what each particle is doing. The only way to capture their quantum state is through equations that describe them together as part of an indivisible whole. Modern laboratories have mastered the art of creating these quantum partnerships through increasingly sophisticated methods. One of the most elegant techniques involves shooting laser light through special crystals that split single photons into pairs of entangled daughter photons. The original photon's energy gets divided between the two new photons, but their quantum properties remain perfectly correlated. These photon twins emerge from the crystal sharing polarization states that mirror each other in precise opposition. The moment of entanglement creation is itself a quantum event, shrouded in superposition. The crystal doesn't decide which specific photons to create at any particular instant. Instead, it maintains a quantum probability cloud of all possible photon pairs it might generate, with each potential pair existing in superposition until detection equipment forces the quantum system to actualize specific particles with definite properties. Scientists have also learned to entangle particles by bringing them close enough to interact, and then carefully separating them while preserving their quantum correlation. Atoms can be trapped in magnetic fields and cooled to temperatures approaching absolute zero, creating conditions where their quantum properties become dominant. When two such atoms interact briefly, they can become entangled in ways that persist even after they're moved apart by substantial distances. The preservation of entanglement requires extraordinary delicacy because quantum correlations are fragile things that can be destroyed by almost any interaction with the environment. Random collisions with air molecules, stray electromagnetic fields, or even tiny vibrations can break the invisible threads connecting entangled particles. This process, called decoherence, represents one of the greatest challenges in quantum technology development. Yet when entanglement does survive, it creates correlations that seem to mock our understanding of space and time. The measurement of one entangled particle instantly determines the state of its partner, regardless of the distance between them. This isn't a gradual influence that propagates across space, but a simultaneous collapse of the shared superposition state that encompasses both particles at once. The mechanics of this instant correlation reveal the true strangeness of quantum entanglement. Before measurement, both particles exist in superposition, with each particle simultaneously embodying all possible states it could be found in. The shared entangled state ensures that these superpositions are perfectly anti-correlated, so that whatever state one particle chooses when measured, its partner must choose the opposite state. When measurement equipment interacts with the first particle, it forces the entire entangled system to collapse from its ghostly superposition into a definite reality. This collapse doesn't respect the limitations of space and time that govern classical physics. The selection of one particle's state instantly determines its partner's state, creating a coordination that appears to transcend the speed of light. Scientists have confirmed this instantaneous correlation through countless experiments involving entangled particles separated by ever-increasing distances. Photon pairs have been entangled across laboratory tables, between buildings, from Earth to satellites in orbit, and through optical fibers spanning hundreds of miles. In every case, measuring one photon's polarization instantly determines its partner's polarization with perfect anti-correlation. The creation of entanglement between larger and more complex quantum systems represents one of the most exciting frontiers in modern physics. Researchers have successfully entangled individual atoms, small groups of atoms, and even microscopic objects visible to the naked eye. Each step toward larger entangled systems brings us closer to understanding how quantum correlations might scale up to influence the classical world we experience every day. Recent experiments have achieved entanglement between tiny mechanical oscillators made of silicon, each about the size of a bacterium. These microscopic beams can vibrate up and down like plucked guitar strings, and scientists have learned to prepare them in quantum superpositions of different vibrational states. When two such oscillators become entangled, they share a combined quantum state where the vibrations of one instantly correlate with the vibrations of the other, regardless of physical separation. The implications of scaling entanglement to larger systems stretch the imagination. If microscopic objects can become quantum partners, what prevents larger objects from sharing the same mysterious connections? Some theorists speculate that entanglement might naturally occur between quantum systems throughout the universe, creating an invisible web of correlations that connects particles across cosmic distances. Every interaction between quantum particles creates the potential for entanglement. And since everything in the universe is ultimately made of quantum particles, every collision, every chemical reaction, every moment of physical contact generates new entangled pairs. Most of these correlations are quickly destroyed by environmental decoherence, but some might persist long enough to create lasting connections between widely separated regions of space. The mathematics describing entangled particles reveals that their shared quantum state contains more information than the sum of information that could be stored in each particle individually. This strange property, called quantum non-locality, suggests that entangled systems represent a fundamentally new kind of physical reality that cannot be understood by analyzing their components separately. The dance of entangled particles creates a choreography that seems to violate our basic intuitions about how separate objects should behave. When quantum partners share their ghostly waltz across the cosmos, they demonstrate that the universe operates through connections deeper than any classical physics predicted. These invisible threads of correlation weave through the fabric of reality itself, linking particles that once shared a moment of interaction into eternal quantum partnerships that transcend the boundaries of space and time. The birth of each entangled pair adds new connections to the growing web of quantum correlations that spans the universe. From the microscopic realm where individual photons become cosmic twins, to the cosmic scale where entire galaxies might share quantum histories, entanglement transforms our understanding of what it means for objects to be separate. In the quantum cosmos, separation itself becomes an illusion, and every measurement participates in the ongoing creation of a reality built from the intimate connections between particles that refuse to forget their shared origins. Chapter 3: Bell's Revolutionary Test. Proving Einstein wrong. In 1964, a brilliant Irish physicist named John Bell accomplished something that Einstein thought impossible. Bell discovered a way to test whether the universe truly operated through spooky action at a distance, or whether Einstein's hidden variable theories could explain the mysterious correlations between entangled particles. This wasn't just another theoretical argument between competing interpretations of quantum mechanics. Bell had found a mathematical method to force nature itself to reveal which vision of reality was correct. Bell's breakthrough came from a profound insight about the nature of correlations between separated particles. If Einstein was right about hidden variables, then entangled particles would carry secret instructions that determined how they should behave when measured. These hidden instructions would need to be incredibly sophisticated, telling each particle exactly how to respond to any possible measurement without requiring any communication between the particles after separation. The genius of Bell's approach was recognizing that hidden variable theories, no matter how cleverly designed, would always be limited by a fundamental constraint. Since the hidden variables had to be determined at the moment of particle separation, and since no information could travel faster than light between the separated particles, the correlations between measurement results would be bounded by mathematical limits that Bell could calculate precisely. Bell constructed what became known as Bell inequalities, mathematical expressions that any theory based on local hidden variables must satisfy. These inequalities set upper limits on how strongly correlated the measurement results from separated particles could be if the particles were only following predetermined instructions without any spooky action at a distance. But quantum mechanics predicted something extraordinary. For certain types of measurements on entangled particles, quantum theory predicted correlations that would violate Bell's inequalities, producing stronger correlations than any local hidden variable theory could explain. If experiments could confirm these violations, it would prove that Einstein's vision of local realism was fundamentally incorrect, and that the universe truly operated through non-local quantum connections. The most famous and widely tested version of Bell's inequality is known as the CHSH inequality, named after John Clauser, Michael Horn, Abner Shimoni, and Richard Holt, who refined Bell's original formulation into a form that was easier to test experimentally. The CHSH inequality focuses on correlations between measurements made along different directions on pairs of entangled particles. Imagine two scientists, traditionally called Alice and Bob, who receive entangled particles and can choose to measure their properties along different axes. Alice might measure her particles spin along a vertical axis or along an axis tilted 30 degrees from vertical. Bob has similar choices for measuring his particle. The CHSH inequality sets a mathematical limit on how correlated their results can be if the particles are following hidden variable instructions. According to local hidden variable theories, the maximum value that can be achieved in CHSH tests is 2. This limit emerges from the fundamental constraint that particles separated in space cannot coordinate their responses to measurements without sending signals between them. Any correlation stronger than this limit would require either faster-than-light communication or genuine non-local connections that transcend space and time. Quantum mechanics, however, predicts that perfectly entangled particles can achieve CHSH values up to approximately 2.83, a number that emerges from the mathematical structure of quantum superposition and entanglement. This quantum maximum represents the strongest possible correlations that can exist between any two separated systems, even in the bizarre quantum realm where particles share ghostly superposition states. The first experimental test of Bell's inequality was performed by John Clauser and Stuart Friedman in 1972. Their experiment used entangled photons created by exciting calcium atoms with electron beams, causing the atoms to emit pairs of photons with correlated polarizations. The results clearly violated Bell's inequality, supporting quantum mechanics over local hidden variable theories. But early Bell tests suffered from experimental limitations that left room for skeptics to argue that the violations might be explained by measurement loopholes rather than genuine quantum non-locality. The most significant concern was the detection loophole, which arose because photon detectors in the 1970s could only capture a small percentage of the photons sent to them. If the detected photons represented a biased sample rather than a random selection, this could artificially create the appearance of Bell inequality violations. Another major concern was the locality loophole, which questioned whether the measurement settings were truly chosen independently of any influence from the entangled particles themselves. If the particles could somehow influence which measurements were performed on them, they might be able to create fake correlations that mimicked genuine quantum entanglement. Alain Aspect and his team in France made crucial progress in the 1980s by performing Bell tests that addressed some of these concerns. Aspect's most famous experiment used rapidly switching measurement devices that changed their settings while the entangled photons were in flight between the source and the detectors. This ensured that the choice of measurement direction was made too late for any light-speed signal to travel from one measurement location to the other, closing the locality loophole. Aspect's results showed clear violations of Bell's inequality with statistical significance that left little room for doubt. The correlations between entangled photons were stronger than any local hidden variable theory could explain, providing compelling evidence that quantum mechanics correctly describe the non-local nature of reality. But skeptics continued to point out that no single experiment had simultaneously closed all possible loopholes. The detection loophole remained a concern because photon detectors still had limited efficiency, and the locality loophole could be more thoroughly closed by using even greater separation distances between measurement locations. The quest to perform truly loophole-free Bell tests drove decades of technological advancement in quantum optics and precision measurement. Scientists needed to develop detectors efficient enough to capture nearly every photon sent to them, while also achieving the timing precision necessary to ensure that measurement choices were made independently of any possible influence from the entangled particles. A major breakthrough came in 2015 when multiple research groups achieved the first loophole-free Bell tests using different experimental approaches. Hansen's team in the Netherlands used entangled electrons trapped in nitrogen vacancy centers in diamond crystals, achieving detection efficiencies high enough to close the detection loophole while maintaining sufficient separation distance to ensure locality. Simultaneously, Anton Zeelinger's group in Austria performed loophole-free tests using entangled photons with highly efficient superconducting detectors, while researchers in the United States used entangled atomic ions with nearly perfect detection efficiency. All of these experiments confirmed Bell inequality violations with overwhelming statistical significance, definitively ruling out local, hidden variable explanations for quantum correlations. The statistical strength of modern Bell test violations leaves no room for reasonable doubt about the non-local nature of quantum entanglement. Typical experiments achieve CHSH values around 2.2 to 2.4, in clearly exceeding the classical limit of 2 while approaching the quantum maximum of approximately 2.83. These violations are observed with statistical significance levels that often exceed 10 standard deviations, meaning the probability of the results occurring by chance is less than 1 in many trillions. Recent experiments have pushed Bell tests to even more extreme conditions, testing quantum non-locality across larger distances and with more complex quantum systems. Chinese researchers have demonstrated Bell inequality violations between Earth and satellites in orbit, proving that quantum correlations persist across hundreds of miles of open space, where no classical mechanism could coordinate the particles' responses. Other experiments have extended Bell tests to more than 2 particles, creating multipartite entangled states, where 3, 4, or even more particles share quantum correlations that violate generalized versions of Bell inequalities. These tests confirm that quantum non-locality scales up to arbitrarily complex systems, suggesting that the entire universe might be connected through invisible webs of quantum correlation. The mathematical framework of Bell inequalities has also been extended to test other fundamental assumptions about reality. Scientists have developed inequalities that test whether measurement results are predetermined before measurement, whether particles have definite properties independent of observation, and whether the choice of measurement direction can influence past events through retrocausal effects. Every experimental test has confirmed the predictions of quantum mechanics, while ruling out alternative theories based on classical intuitions about how reality should behave. The universe consistently demonstrates correlations that exceed classical limits, displaying a level of connectedness that transcends our everyday experience of separate objects interacting through local forces. Modern Bell tests using superconducting quantum circuits have achieved some of the cleanest demonstrations of quantum non-locality by eliminating many of the experimental complications that plagued earlier photon-based experiments. These solid-state quantum systems can be controlled with extraordinary precision, allowing researchers to create nearly perfect entangled states and perform measurements with timing accuracy measured in nanoseconds. The results from superconducting circuit experiments show CHSH violations that approach the theoretical quantum maximum, confirming that artificial quantum systems can exhibit the same non-local correlations as natural quantum phenomena. This technological mastery of quantum entanglement and Bell inequality violations forms the foundation for emerging quantum technologies like quantum computers and quantum communication networks. Bell's theorem has evolved from a philosophical thought experiment into a practical tool for certifying the quantum nature of technological systems. Modern quantum devices must demonstrate Bell inequality violations to prove they're operating in the genuine quantum regime, rather than just simulating quantum behavior through classical processes. This quantum certification has become essential for validating the performance of quantum computers and ensuring the security of quantum cryptographic systems. The implications of Bell's revolutionary test extend far beyond the laboratory. By proving that local hidden variable theories cannot explain quantum correlations, Bell inequality violations demonstrate that the universe operates through connections that transcend space and time. These non-local correlations don't allow faster-than-light communication, but they reveal that reality is fundamentally interconnected in ways that classical physics never anticipated. Einstein's intuition that quantum mechanics seemed too strange to be true was absolutely correct. The universe truly is stranger than classical physics suggested, filled with invisible connections that link separated particles through correlations that exceed any classical limit. But rather than representing a flaw in our understanding, this strangeness has become the foundation for revolutionary new technologies that harness quantum non-locality for practical applications. Bell's legacy lies not just in proving Einstein wrong about hidden variables, but in providing humanity with a mathematical tool for exploring the deepest mysteries of reality. Every Bell test violation confirms that we live in a quantum universe where separation is never complete, where measurement is never purely local, and where the act of observation participates in an ongoing dance of cosmic correlation that connects every particle to the infinite web of quantum entanglement that spans the cosmos. Chapter 4: The impossibility of faster-than-light communication. The most tantalizing question about quantum entanglement isn't whether spooky action at a distance exists, but whether these mysterious connections could allow us to send messages faster than light itself. If measuring one entangled particle instantly affects its cosmic partner anywhere in the universe, why can't we use this connection to build an Ansible, a device that could transmit information instantaneously across galactic distances? The answer reveals one of the most profound and frustrating limitations built into the fabric of reality itself. Science fiction writers have long dreamed of quantum entanglement communicators that would revolutionize interstellar civilization. In novels like the Three Body Problem series, spacefaring empires use entangled particles to maintain instant communication across their vast territories. Video games like Mass Effect feature quantum entanglement communicators as standard equipment for faster-than-light coordination between distant star systems. The appeal of such technology is obvious when you consider that even light takes over 4 years to travel from Earth to the nearest star, making conventional communication painfully slow for any civilization spanning multiple solar systems. The theoretical possibility seems tantalizingly simple. Create pairs of entangled particles on Earth. Send one particle from each pair to distant outposts throughout the galaxy, and use the remaining particles to send instant messages by manipulating their quantum states. When scientists on Earth measure their particles in specific ways, their entangled partners at distant locations would instantly respond, creating a coded signal that could travel faster than any electromagnetic wave. But the universe has built an elegant and unbreakable barrier against this type of faster-than-light communication, and understanding why reveals fundamental truths about the nature of information, randomness, and causality itself. The barrier emerges from the inherently random nature of quantum measurement, which prevents anyone from controlling what results they obtain when measuring entangled particles. To understand why quantum entanglement can't carry messages, imagine Alice on Earth with an entangled particle, and Bob on a distant planet with that particle's quantum twin. Alice wants to send Bob a message by manipulating her particle in ways that will affect Bob's particle. The challenge is that quantum mechanics provides no way for Alice to force her particle into any specific state when she measures it. When Alice measures her particle's spin, quantum mechanics tells us that she will randomly get either spin up or spin down, each with 50% probability. The randomness isn't just a limitation of our measurement technology, it appears to be a fundamental feature of reality itself. Alice cannot choose whether her particle will be measured as spinning up or down. She can only observe which random outcome occurs. This randomness immediately creates an insurmountable problem for faster-than-light communication. If Alice cannot control what result she gets when measuring her particle, she cannot encode any information into that measurement. She might want to send Bob the message, "Attack at dawn," but she has no way to force her particle measurements to create the specific sequence of results needed to spell out those words. Meanwhile, on his distant planet, Bob faces an equally frustrating limitation. When he measures his entangled particle, he will indeed get results that are perfectly correlated with Alice's measurements. If Alice measures spin up, Bob will instantly measure spin down, maintaining the anti-correlated relationship required by their particle's entangled state. But Bob has no way of knowing when Alice has made a measurement versus when she hasn't. From Bob's perspective, his particle produces a completely random sequence of measurement results, sometimes up and sometimes down with no discernible pattern. Even though these results are instantly correlated with Alice's measurements, Bob cannot distinguish between the random results caused by Alice's measurements and the random results that would occur if Alice never measured her particle at all. This creates a communication deadlock that no clever experimental design can overcome. Alice cannot control her measurement results to encode messages, and Bob cannot decode Alice's actions from his random measurement results. The entangled particles maintain their spooky instant correlation, but this correlation carries no usable information that could constitute a message. Scientists have proposed numerous ingenious schemes to work around these limitations, but every attempt runs into the fundamental problem that quantum measurements are genuinely random and that this randomness prevents the encoding and decoding of information. Some proposals involve making measurements along different axes, reasoning that Alice could choose to measure spin along a vertical axis to send a binary 0 or along a horizontal axis to send a binary 1. But even this approach fails because Bob cannot determine which measurement axis Alice chose without comparing notes with her through conventional, slower-than-light communication. When Bob measures his particle, he gets random results regardless of which axis Alice used, because his particle must collapse into some definite state, and the choice of axis affects only the probability distributions, not the ability to distinguish one measurement from another. Other proposed schemes involve more complex manipulations, such as Alice performing a sequence of measurements and trying to create statistical patterns that Bob could detect. But the mathematics of quantum mechanics shows that any statistical pattern Alice creates in her measurement sequence will be masked by the fundamental randomness of Bob's results. Bob's measurements will always appear completely random to him, regardless of what Alice does with her particle. The no communication theorem provides a rigorous mathematical proof that quantum entanglement cannot transmit information faster than light. This theorem shows that the statistical properties of Bob's measurement results are completely independent of any actions Alice performs on her entangled particle. From Bob's perspective, his particle behaves exactly as if it were not entangled at all, producing random results that contain no trace of Alice's activities. This impossibility of faster-than-light communication through quantum entanglement emerges from the same quantum randomness that makes Bell inequality violations possible. The correlations between entangled particles are real and instantaneous, but they can only be detected when Alice and Bob compare their measurement results through conventional communication channels. The instant correlation exists, but detecting it requires slower-than-light information exchange. The frustrating paradox is that quantum entanglement creates genuine, faster-than-light correlations, while simultaneously preventing any practical use of these correlations for sending messages. The universe seems to be teasing us with a phenomenon that appears to violate the speed of light limit, while carefully ensuring that this violation cannot be exploited to actually transmit information faster than light. This limitation becomes even more apparent when we consider what would happen if faster-than-light communication were possible through quantum entanglement. Such communication would immediately create paradoxes that would undermine the logical foundation of physics itself. If Alice could send Bob a message faster than light, then according to Einstein's theory of relativity, there would be reference frames where Bob would receive the message before Alice sent it. These causality violations would lead to grandfather paradox-style contradictions, where effects could precede their causes. Bob could use his faster-than-light communicator to send a message back to Alice, warning her not to send the original message, creating a logical loop that has no consistent resolution. The universe appears to protect itself against such paradoxes by ensuring that quantum correlations, while real and instantaneous, cannot carry information. The randomness that prevents faster-than-light communication also reveals something profound about the nature of quantum mechanics itself. Unlike classical physics, where random events arise from our ignorance of underlying deterministic processes, quantum randomness appears to be fundamental. No hidden variables or deeper theories can eliminate this randomness without destroying the quantum correlations that make entanglement possible. Einstein's famous objection that God does not play dice with the universe was based on his belief that quantum randomness must be the result of incomplete knowledge rather than fundamental uncertainty. But experiments have confirmed that the universe truly does seem to play dice, using quantum randomness as a basic feature of reality rather than an unfortunate limitation of our understanding. This quantum randomness serves as the universe's protection mechanism against causality violations. By ensuring that no one can control the outcomes of quantum measurements, nature prevents the faster-than-light communication that would lead to logical paradoxes. The same randomness that frustrated Einstein becomes the safeguard that preserves the consistency of physical law across all reference frames. The mathematical structure of quantum mechanics reveals why this protection is so robust. The quantum states of entangled particles are described by complex mathematical objects that contain correlations between measurement outcomes while ensuring that the individual outcomes remain fundamentally unpredictable. These correlations can be stronger than any classical theory allows, but they cannot be used to transmit information because information requires the ability to choose between different messages. Modern experiments have pushed against these limitations with increasing sophistication, testing whether advanced quantum control techniques might open loopholes for faster-than-light communication. Researchers have explored whether quantum error correction, quantum feedback control, or measurements on more complex entangled states might provide ways to encode information into quantum correlations. Every experimental test has confirmed the no communication theorem. No matter how cleverly scientists design their quantum communication schemes, the fundamental randomness of quantum measurement always prevents the transmission of information faster than light. The universe maintains its protection against causality violations with remarkable consistency across all tested scenarios. Interestingly, the same quantum mechanics that prohibits faster-than-light communication also provides the foundation for revolutionary new technologies that exploit quantum correlations for practical applications. Quantum cryptography uses entangled particles to create unbreakable encryption systems, even though these systems cannot transmit information faster than light. Quantum computing harnesses entanglement to perform certain calculations exponentially faster than classical computers, despite being unable to communicate faster than light. These technologies demonstrate that quantum correlations, while unsuitable for faster-than-light messaging, provide other advantages that classical physics cannot match. The universe seems to offer quantum mechanics as a package deal, providing extraordinary new capabilities while maintaining strict limits on information transmission that preserve the logical consistency of space-time. The relationship between quantum mechanics and Einstein's theory of relativity reveals a remarkable harmony between two theories that were developed independently and describe vastly different scales of reality. Quantum mechanics governs the microscopic world of atoms and particles, while relativity describes the cosmic scale behavior of space, time, and gravity. Yet both theories independently arrive at the same conclusion about the speed of information transfer. Einstein's relativity shows that faster-than-light communication would violate causality by allowing effects to precede their causes in certain reference frames. Quantum mechanics shows that entangled particles cannot carry information faster than light, because quantum measurements are fundamentally random. Two completely different theoretical frameworks, developed from different starting points, converge on the same fundamental limit. This convergence suggests that the speed of light limit for information transmission is not just an arbitrary rule imposed by one theory, but a deep feature of reality itself that emerges from the logical requirements of consistent physics. The universe appears to be constructed in such a way that faster-than-light communication is not just practically difficult, but logically impossible. The impossibility of quantum communication faster than light reveals that Einstein was both wrong and right in profound ways. He was wrong about quantum mechanics being incomplete and about hidden variables being able to explain quantum correlations. But he was right that the speed of light represents a fundamental limit on information transmission. And he was right that the universe operates according to logical principles that prevent paradoxes and contradictions. The cosmic dance of entangled particles continues across all distances, maintaining their spooky instant correlations while carefully ensuring that these correlations cannot be exploited to violate the causal structure that Einstein's relativity revealed. The universe gives us quantum entanglement as a glimpse into the deep connectedness of reality, while preserving the logical consistency that makes science itself possible. In this delicate balance between connection and causality, we find one of the most beautiful and mysterious features of the quantum cosmos. Chapter 5: Spooky action in the largest and smallest scales. For most of the 20th century, scientists believed that quantum entanglement was exclusively a microscopic phenomenon, confined to the strange realm of individual atoms and subatomic particles, where classical physics breaks down. The idea that spooky action at a distance could operate on larger scales seemed impossible, because bigger objects should be too noisy and too connected to their environment to maintain the delicate quantum correlations that make entanglement possible. But in the 21st century, researchers have shattered these assumptions by discovering quantum entanglement operating at scales ranging from the largest particles ever detected to the smallest distances imaginable within individual protons. The breakthrough into macroscopic quantum entanglement began with experiments that pushed the boundaries of what physicists thought possible. Simon Groblecker and his team at Delft University of Technology in the Netherlands created a quantum marvel by etching tiny silicon beams about 10 micrometers long into computer chips. These microscopic structures, roughly the size of bacteria, could oscillate up and down like impossibly small guitar strings vibrating in quantum superposition. The engineering required to achieve entanglement between these macroscopic quantum objects pushed technology to its absolute limits. The researchers had to cool their entire experimental setup to temperatures approaching absolute zero, creating conditions colder than the depths of interstellar space to prevent random thermal vibrations from destroying the delicate quantum correlations. In this frozen quantum laboratory, the silicon beams could enter superposition states where they simultaneously vibrated and remained still, existing in ghostly overlays of motion and stillness. By connecting their silicon chips with optical fibers and using precisely controlled laser pulses, Groblecker's team achieved something that seemed impossible according to classical physics. They created entangled states where the vibrational energy was shared between the two microscopic beams in quantum superposition. When they added energy to make one beam vibrate more strongly, the quantum measurement revealed that this energy existed in superposition across both beams simultaneously, even though the beams were physically separated and connected only by optical fibers. The entangled state lasted only a fraction of a second before environmental interference destroyed the quantum correlations. But this brief moment of macroscopic entanglement represented a revolutionary step toward understanding how quantum phenomena might scale up to influence the everyday world. The fact that objects large enough to be visible under powerful microscopes could share quantum correlations suggested that the boundary between the quantum and classical worlds might be far more fluid than anyone had imagined. Meanwhile, Mika, Sillanpää's research group at Aalto University in Finland, took a different approach to macroscopic entanglement by creating pairs of aluminum drumheads about the width of human hairs. These microscopic drums could vibrate up and down in coordinated quantum rhythms, with one drum's motion instantly correlated with its partner's motion through quantum entanglement. The researchers used carefully controlled microwave pulses to nudge the drumheads into correlated quantum motions, where measuring one drum's vibration would instantly determine the vibrational state of its partner. These experiments in macroscopic quantum entanglement opened the door to applications that could revolutionize precision measurement and sensing technology. Because quantum correlations can be more sensitive to external disturbances than classical correlations, entangled macroscopic objects could serve as incredibly precise detectors for gravitational waves, magnetic fields, or other subtle influences that classical sensors might miss. But perhaps the most shocking discovery about quantum entanglement came from experiments at the largest particle accelerator on Earth, where scientists found spooky action at a distance operating between the heaviest fundamental particles known to exist. At CERN's Large Hadron Collider near Geneva, Switzerland, researchers detected quantum entanglement between top quarks and their antimatter partners, proving that quantum correlations can persist even among particles as massive as gold atoms. Top quarks are extraordinary particles that exist for less than a trillionth of a second before decaying into lighter particles. They are so heavy and so short-lived that they can only be created in the most powerful particle accelerators ever built, where protons smash together at energies approaching the conditions that existed moments after the Big Bang. Yet even in this violent, high-energy environment, quantum entanglement emerges between top quark pairs, creating instant correlations between particles moving at substantial fractions of the speed of light. The CERN experiments revealed that entangled top quarks maintain their quantum correlations even when they separate by distances larger than what light could travel during their brief lifetimes. This means the particles demonstrate genuine spooky action at a distance, with correlations that cannot be explained by any classical signal or hidden variable traveling between them. The discovery proves that quantum entanglement operates even among the most massive and energetic particles that high-energy physics can create. Regina Demener's research group at the University of Rochester played a crucial role in analyzing the CERN data that revealed top quark entanglement. Their statistical analysis showed correlations between the spin orientations of top quarks and their antimatter partners that violated Bell inequalities with high significance, providing clear evidence for quantum non-locality operating in the extreme environment of high-energy particle collisions. The implications of top quark entanglement extend far beyond particle physics laboratories. These experiments suggest that quantum correlations were present in the earliest moments after the Big Bang, when the universe was filled with high-energy particles similar to those created in modern accelerators. If entanglement could survive in the violent conditions of particle collisions, it might have played a fundamental role in shaping the structure and evolution of the cosmos itself. Even more remarkable discoveries emerged from experiments probing the internal structure of protons, the positively charged particles found in every atomic nucleus. Using high-energy electron-proton collisions, scientists mapped out quantum entanglement operating at distances less than 1/quadrillionth of a meter inside individual protons. This represents spooky action at a distance operating on the smallest scale ever directly observed, where quantum correlations connect the quarks and gluons that form protons' internal structure. The experiments revealed that quarks and gluons within protons are subject to quantum entanglement that influences how particles emerge from high-energy collisions. The entanglement affects the angular distributions of particles, created when electrons smash into protons, creating patterns that can only be explained by quantum correlations operating within the proton's internal structure. This discovery shows that every proton in every atom in your body contains quantum entanglement operating at unimaginably small scales. Understanding entanglement within protons has become crucial for planning experiments at the Future Electron-Ion Collider, a nuclear physics research facility expected to open at Brookhaven National Laboratory in the 2030s. This next-generation accelerator will probe how quantum entanglement affects nuclear structure, and how being part of a larger atomic nucleus influences the quantum correlations within individual protons and neutrons. The scale of quantum entanglement discoveries stretches from the incredibly small to the potentially cosmic. Theoretical physicists have proposed that the entire observable universe might have emerged from a maximally entangled quantum state during the first moments after the Big Bang. In this scenario, every particle in the cosmos would have started in quantum correlations with every other particle, creating a universal web of entanglement that connected all matter across space. Most of this primordial entanglement would have been destroyed by the rapid expansion of space and the countless interactions between particles as the universe cooled and evolved. But traces of the original quantum correlations might still persist in the cosmic microwave background radiation that fills the universe, creating subtle patterns that could be detected by sensitive astronomical instruments. The process of decoherence, which destroys quantum entanglement through interaction with the environment, played a crucial role in the universe's evolution from a quantum state to the classical reality we observe today. As the universe expanded and cooled, random interactions between particles gradually broke most of the quantum correlations that existed in the early cosmos, allowing classical behavior to emerge on large scales while preserving quantum effects in isolated microscopic systems. Some researchers speculate that consciousness itself might have emerged as a way for the universe to observe and collapse quantum superpositions, playing an active role in the transition from quantum to classical behavior. In this view, the development of conscious observers represents a new phase in cosmic evolution, where the universe begins to observe itself through quantum measurements performed by living beings. Recent discoveries have also revealed quantum entanglement operating in biological systems, suggesting that living organisms might naturally harness quantum correlations for enhanced efficiency in fundamental life processes. Experiments have detected quantum coherence in the photosynthesis systems of plants and bacteria, where entangled quantum states might help organisms capture and transfer energy with near-perfect efficiency. Birds appear to use quantum entanglement in specialized proteins within their eyes to navigate using Earth's magnetic field. The quantum correlations between entangled particles in these proteins could provide birds with a quantum compass that allows them to sense magnetic field directions with extraordinary precision. This biological quantum sensing demonstrates that evolution has discovered ways to exploit quantum phenomena for practical advantages in the classical world. The human brain itself might operate through quantum processes that involve entanglement between networks of neurons. Some theories of consciousness propose that quantum correlations within microtubules inside brain cells could give rise to conscious experience through quantum information processing that transcends classical computation. While these ideas remain speculative, growing evidence suggests that quantum effects play important roles in biological systems at all scales. Quantum entanglement has also been detected in synthetic materials designed to exploit quantum correlations for technological applications. Researchers have created quantum dots, superconducting circuits, and other artificial quantum systems that can maintain entanglement under conditions that would be impossible for natural quantum systems. These engineered quantum materials form the foundation for emerging quantum technologies, like quantum computers and quantum sensors. The scalability of quantum entanglement suggests that the boundary between quantum and classical physics is far more permeable than early 20th century physicists imagined. Rather than being confined to individual atoms and molecules, quantum correlations can operate across a vast range of scales. From the internal structure of protons to macroscopic mechanical oscillators to potentially cosmic distances. Modern experiments continue to push the limits of how large and how far apart entangled quantum systems can be, while maintaining their correlations. Chinese researchers have demonstrated quantum entanglement between Earth and satellites in orbit, proving that quantum correlations can survive transmission through hundreds of miles of space, where cosmic radiation and atmospheric interference could potentially destroy the delicate quantum connections. The robustness of quantum entanglement across different scales and environments reveals that quantum correlations represent a fundamental feature of reality, rather than a fragile curiosity confined to laboratory conditions. The universe appears to be naturally quantum at all scales, with classical behavior emerging as an approximation that works well for large, warm objects, but breaks down when we probe the deeper structure of reality. Future experiments will test quantum entanglement across even larger scales and more extreme conditions, potentially revealing quantum correlations operating between distant galaxies or within the event horizons of black holes. These cosmic scale tests of quantum entanglement could provide new insights into the relationship between quantum mechanics and gravity, two fundamental theories that scientists are still working to unify into a complete description of reality. The discovery of quantum entanglement, operating from the smallest to the largest scales, transforms our understanding of what it means for objects to be separate in space. At every level of reality, from quarks within protons to mechanical oscillators in laboratories, to potentially entire galaxies connected by shared quantum histories, the universe reveals itself to be an interconnected web of correlations that transcend the classical boundaries of space and time. In this quantum cosmos, separation becomes an illusion, and every measurement participates in a dance of correlation that connects the observer to the infinite network of quantum entanglement that spans all scales of existence. Chapter 6: Your Quantum Self. Entanglement in Human Consciousness. Deep within the warm, wet environment of your brain, something extraordinary might be happening that connects your consciousness to the quantum fabric of the universe itself. While most scientists have assumed that biological systems are too noisy and chaotic to support the delicate quantum effects that create entanglement, a growing body of research suggests that evolution has discovered ways to harness quantum mechanics for the most fundamental processes of life, including the mysterious emergence of conscious awareness. Every moment you think a thought, make a decision, or become aware of your surroundings, billions of neurons in your brain fire in precisely coordinated patterns that somehow give rise to the unified experience of consciousness. The mechanisms underlying this transformation from neural activity to subjective awareness remain one of the deepest mysteries in science, but quantum entanglement might provide the missing link that explains how separate brain cells combine into a single, unified conscious experience. The human brain contains approximately 86 billion neurons, each connected to thousands of others through intricate networks that process information with extraordinary efficiency. Classical theories of consciousness assume that these neurons communicate through purely chemical and electrical signals, with consciousness emerging from the complex patterns of activity that arise when billions of cells interact according to the laws of classical physics. But classical theories struggle to explain how the separate activities of individual neurons combine into the unified field of consciousness that characterizes human experience. When you look at a red rose, millions of different neurons respond to various aspects of the visual scene, detecting edges, colors, shapes, and patterns. Yet somehow, these distributed neural responses combine into a single, coherent conscious experience of seeing a beautiful flower. Quantum theories of consciousness propose that the unity of conscious experience emerges from quantum entanglement between networks of neurons that become quantum mechanically correlated during the process of information integration. Rather than existing as separate classical objects that communicate through chemical signals, neurons might share quantum correlations that allow them to participate in collective quantum states that transcend individual cellular boundaries. The most detailed quantum theory of consciousness focuses on microscopic structures, called microtubules, that exist within the interior of every neuron. These protein assemblies form the cellular skeleton that gives neurons their shape, but they might also function as quantum information processing systems that operate at temperatures and timescales where quantum effects could survive, despite the warm, noisy environment of living tissue. Microtubules are composed of proteins called tubulins that can exist in different structural configurations, creating binary states similar to the bits used in classical computers. But unlike classical bits, tubulin proteins might exist in quantum superpositions, where they simultaneously occupy multiple configurations, creating quantum bits or qubits that could process information through quantum mechanical principles. Roger Penrose and Stuart Hameroff have proposed that consciousness emerges when quantum computations within microtubule networks reach a threshold that triggers the collapse of quantum superpositions into definite states. In their theory, conscious moments correspond to orchestrated quantum state reductions that occur when the quantum information processing within neurons reaches a critical level of complexity and coherence. This orchestrated objective reduction theory suggests that consciousness involves genuine quantum measurements performed by biological systems, with each moment of awareness corresponding to a quantum collapse event that selects one possibility from the superposition of potential conscious states. The theory predicts that consciousness operates through discontinuous quantum jumps rather than the smooth, continuous processes assumed by classical theories. Recent experiments have provided surprising evidence that quantum effects might indeed operate within biological systems under conditions that were previously thought to destroy quantum coherence. The most compelling discoveries come from studies of photosynthesis, the process by which plants and bacteria convert sunlight into chemical energy with extraordinary efficiency that approaches the theoretical limits of what classical physics would allow. In photosynthetic systems, energy from absorbed photons must travel through complex molecular networks to reach reaction centers where chemical conversion occurs. Classical physics predicts that this energy transfer should be relatively inefficient because random thermal motion would cause energy to be lost as heat during transport. But experiments reveal that photosynthetic systems achieve near-perfect energy transfer efficiency through quantum coherence effects that allow energy to explore multiple pathways simultaneously. Quantum coherence in photosynthesis operates through superposition states where absorbed energy exists simultaneously across multiple molecular locations, allowing the system to find the most efficient pathway to the reaction center through quantum mechanical exploration of all possibilities. This biological quantum computation occurs at room temperature in the presence of thermal noise that classical physics suggests should destroy quantum effects within femtoseconds. The discovery that biological systems can maintain quantum coherence under physiological conditions has revolutionized thinking about the potential for quantum effects in living organisms. If plants and bacteria can harness quantum mechanics for energy transfer, more complex biological systems like nervous systems might also exploit quantum phenomena for information processing and conscious awareness. Birds provide another compelling example of biological quantum mechanics through their ability to navigate using Earth's magnetic field with extraordinary precision. European robins and other migratory species appear to possess a quantum compass within specialized proteins in their eyes that allows them to sense magnetic field directions through quantum entanglement between pairs of electrons. The avian magnetic compass operates through pairs of electrons that become entangled when light strikes cryptochrome proteins in the bird's retinas. Earth's magnetic field influences the quantum correlations between these entangled electrons, creating different patterns of chemical reactions that the birds can detect as visual signals. This biological quantum sensor allows birds to literally see magnetic field lines as overlay patterns on their visual perception of the world. Experiments with robins have confirmed that their magnetic navigation abilities are disrupted by radio frequency electromagnetic fields that would not affect classical magnetic sensors, but could interfere with the delicate quantum correlations that enable quantum magnetic sensing. This provides strong evidence that bird navigation relies on genuine quantum mechanical processes rather than classical magnetic detection mechanisms. The human brain might contain similar quantum sensing systems that operate through entangled electron pairs in neural proteins. Some researchers propose that quantum entanglement between electrons in neural microtubules could create networks of quantum correlation that span entire brain regions, allowing widely separated neurons to share quantum information instantaneously. Quantum entanglement in neural networks could explain some of the most puzzling features of consciousness, including the unity of conscious experience and the apparent non-locality of memory and recognition. When you remember a childhood experience, information seems to become available across your entire conscious field simultaneously, rather than propagating through your brain at the finite speeds that characterize classical neural communication. If consciousness involves quantum entanglement between neural networks, then remembering could involve the collapse of quantum superpositions that instantaneously correlate activity across multiple brain regions. The quantum correlations would allow spatially separated neurons to participate in unified conscious states that transcend the classical limitations of neural communication speed. Quantum theories of consciousness also suggest that the process of making decisions might involve genuine quantum randomness rather than deterministic classical computation. When you choose between different options, your brain might be performing quantum measurements that collapse superposition states of potential decisions into definite choices through fundamentally random quantum processes. This quantum indeterminacy in decision-making could provide a physical basis for free will that is neither completely determined by prior causes nor completely random. Quantum consciousness theories propose that conscious choice emerges from quantum measurements that are influenced by but not completely determined by the classical neural activity that precedes decisions. Recent experiments using sophisticated brain imaging techniques have detected neural correlates of consciousness that exhibit some features consistent with quantum information processing. Studies of visual consciousness show that when people become aware of previously unconscious visual stimuli, neural activity patterns change in ways that resemble quantum phase transitions rather than gradual classical state changes. The timing of conscious perception also exhibits characteristics that are difficult to explain using classical neural processing. Consciousness appears to involve backward-in-time effects, where later neural events influence the timing and content of earlier conscious experiences, creating temporal correlations that resemble the retrocausal effects predicted by some interpretations of quantum mechanics. Anesthesia research has revealed that the loss of consciousness during medical procedures involves changes in neural network connectivity that might reflect the disruption of quantum correlations between brain regions. Some anesthetic agents appear to specifically interfere with microtubule function, supporting the hypothesis that consciousness depends on quantum processes within these cellular structures. Studies of patients with split brain conditions, where connections between the brain's hemispheres have been surgically severed, reveal that consciousness can divide into separate streams of awareness that seem to operate independently. This divisibility of consciousness is consistent with quantum theories that predict conscious unity emerges from quantum entanglement networks that can be physically disrupted. The relationship between consciousness and quantum entanglement extends beyond individual brains to encompass potential quantum correlations between different conscious observers. Some theories propose that conscious observers can become quantum entangled through shared experiences, creating interpersonal quantum correlations that might explain phenomena like empathy, emotional contagion, and collective consciousness. If consciousness involves quantum measurements of brain states, then the act of one person observing another's behavior could create quantum entanglement between the observer and the observed through the shared quantum events involved in conscious perception. This interpersonal quantum entanglement could provide a physical mechanism for the deep sense of connection that people sometimes experience during intimate conversations or shared emotional experiences. Meditation and other contemplative practices might also involve alterations in neural quantum coherence that expand conscious awareness beyond the normal boundaries of individual identity. Advanced meditators report experiences of expanded consciousness, where the sense of separation between self and world dissolves, potentially reflecting quantum entanglement between neural networks and environmental quantum systems. The measurement problem in quantum mechanics, which concerns how quantum superpositions collapse into definite states, might be intimately connected to the emergence of consciousness in biological systems. Some interpretations of quantum mechanics propose that consciousness plays a fundamental role in quantum measurement, suggesting that the evolution of conscious observers represents a new phase in cosmic evolution where the universe begins to observe itself. If consciousness involves quantum entanglement between neural networks, then every conscious moment represents a quantum measurement event that participates in the ongoing collapse of cosmic quantum superpositions. Your thoughts, perceptions, and decisions would be directly connected to the fundamental quantum processes that determine the evolution of reality itself. The implications of quantum consciousness extend beyond individual human experience to encompass the possibility that consciousness is a fundamental feature of the universe that emerges whenever quantum systems reach sufficient complexity and coherence. Rather than being an accidental byproduct of neural evolution, consciousness might represent the universe's method of observing and actualizing quantum possibilities into definite realities. Modern research continues to probe the boundaries between quantum mechanics and biological systems, using increasingly sophisticated techniques to detect quantum effects in living tissue. Experiments with quantum sensors are beginning to map the magnetic fields and electrical currents within functioning brains with unprecedented precision, potentially revealing signatures of quantum information processing in neural networks. The possibility that consciousness emerges from quantum entanglement between neural networks suggests that your thoughts and experiences are directly connected to the quantum fabric of reality itself. Every moment of awareness might involve quantum correlations that link your consciousness to the cosmic web of entanglement that spans the universe, making you an active participant in the ongoing quantum evolution of reality rather than a passive observer of a predetermined classical world. In this quantum vision of consciousness, the spooky action at a distance that Einstein found so troubling becomes the very mechanism through which awareness emerges from matter, connecting individual minds to the universal network of quantum correlation that underlies all existence. Your consciousness doesn't just observe the quantum universe, it participates in its creation through every moment of quantum entangled awareness that collapses possibility into actuality. Chapter 7: Building the Quantum Internet. Technology of Cosmic Connection. In laboratories around the world, scientists are building the first networks of a revolutionary new internet that will transform human communication forever. Unlike the classical internet that connects computers through electrical signals and radio waves, this quantum internet harnesses the spooky action at a distance that Einstein found so troubling to create connections that are fundamentally unbreakable and instantaneously secure. Every message sent through quantum entanglement carries an intrinsic protection that makes eavesdropping not just difficult, but physically impossible according to the laws of quantum mechanics themselves. The foundation of quantum communication lies in the extraordinary properties of entangled particles that maintain their mysterious correlations across any distance. When two particles become quantum entangled, they share a connection so intimate that any attempt to intercept or measure their quantum states instantly reveals itself to both the sender and receiver. This quantum surveillance detection emerges from the fundamental fragility of quantum superposition states, which collapse the moment any outside system tries to observe them. Traditional internet security relies on mathematical complexity, using encryption algorithms that would take classical computers millions of years to crack. But these systems remain vulnerable to more powerful computers or clever mathematical breakthroughs that could render current encryption methods obsolete. Quantum communication offers something far more powerful: security guaranteed by the laws of physics themselves, which no amount of computational power or mathematical insight can overcome. The Chinese quantum satellite program has achieved some of the most impressive demonstrations of long-distance quantum communication ever attempted. In 2016, China launched MISSIUS, the world's first quantum communication satellite, named after an ancient Chinese philosopher who conducted some of the earliest experiments with light and optics. This groundbreaking satellite has successfully distributed entangled photons between ground stations, separated by over 1,000 miles, proving that quantum correlations can survive transmission through the vacuum of space. The satellite experiments work by creating pairs of entangled photons in orbit and beaming one photon from each pair to different ground stations on Earth's surface. The entangled photons maintain their quantum correlations despite traveling through hundreds of miles of space and Earth's atmosphere, which contains moisture, dust, and thermal turbulence that could potentially disrupt delicate quantum states. The success of these space-based experiments proves that quantum communication can operate under real-world conditions far more challenging than controlled laboratory environments. Ground-based quantum networks have also achieved remarkable progress in extending the range and reliability of quantum communication systems. The Chinese quantum network connecting Beijing and Shanghai spans over 1,000 miles of optical fiber cables, creating the longest quantum communication link ever established on Earth's surface. This network demonstrates that quantum key distribution can operate over continental distances using existing telecommunications infrastructure. European researchers have built their own quantum communication networks linking major cities across the continent, while teams in the United States have created quantum links between government facilities and research institutions. These early quantum networks serve as testbeds for developing the technologies and protocols that will eventually enable a global quantum internet connecting every major population center on Earth. The basic principle of quantum key distribution reveals how quantum entanglement creates unbreakable security through the fundamental properties of quantum measurement. When Alice wants to send Bob a secure message, they first establish a shared secret key using entangled particles that only they can access. Alice and Bob each receive one particle from entangled pairs, then perform measurements on their particles using randomly chosen orientations. The quantum mechanics of entangled particles ensures that Alice and Bob's measurement results are perfectly correlated when they choose the same measurement orientations, but completely random when they choose different orientations. By comparing a small sample of their results through classical communication, Alice and Bob can determine which measurements they performed using matching orientations, allowing them to extract a shared secret key from the correlated results. Any eavesdropper attempting to intercept the quantum key distribution would inevitably disturb the entangled particles, introducing errors that Alice and Bob can detect by monitoring the correlation statistics of their measurement results. The quantum no-cloning theorem ensures that no one can make perfect copies of unknown quantum states, preventing eavesdroppers from capturing quantum information without leaving detectable traces of their interference. This intrinsic security of quantum communication emerges from the fundamental randomness of quantum measurement combined with the fragility of quantum entanglement. The same properties that prevent faster-than-light communication also make quantum communication channels impossible to tap without detection. The universe's protection against causality violations also protects quantum messages against unauthorized access. Modern quantum key distribution systems have achieved impressive levels of practical security and reliability, with some networks operating continuously for months while maintaining error rates low enough to guarantee security against any conceivable eavesdropping attempt. Commercial quantum communication companies now offer quantum key distribution services to banks, government agencies and corporations that require the highest levels of data security. The next major challenge in quantum communication involves extending quantum networks beyond the current limitations of direct point-to-point connections. Quantum signals cannot be amplified like classical signals, because any attempt to measure and regenerate quantum states would destroy the quantum information they carry. Instead, quantum networks require quantum repeaters that can extend entanglement across long distances without measuring the quantum states directly. Quantum repeaters work by creating chains of entangled particles that connect distant locations through intermediate nodes. Each repeater station stores quantum information in quantum memory devices that can hold entangled states for extended periods, while coordination protocols establish entanglement links across the entire network. Once the chain of entanglement connections is complete, quantum teleportation protocols can transfer quantum information from one end of the network to the other. Quantum teleportation represents one of the most remarkable applications of quantum entanglement for practical communication technology. Despite its science fiction-sounding name, quantum teleportation doesn't involve transporting matter or energy across space. Instead, it transfers the complete quantum information, describing an unknown quantum state from one location to another, using entangled particles as a quantum communication channel. The teleportation process begins with an entangled pair of particles shared between the sender and receiver. The sender performs a special type of quantum measurement that compares the unknown quantum state they want to teleport with their half of the entangled pair. This measurement destroys the original quantum state while extracting classical information about how it relates to the entangled particle. The sender transmits this classical information to the receiver through conventional communication channels. The receiver uses this classical information to perform specific quantum operations on their half of the entangled pair, which transforms their particle into an exact replica of the original quantum state that was destroyed at the sender's location. The unknown quantum state has been teleported from sender to receiver without ever existing in the space between them. Quantum teleportation experiments have successfully transferred quantum states between laboratory equipment, between buildings, and across distances of hundreds of miles using optical fibers and satellite links. Recent experiments have achieved teleportation fidelities exceeding 99%, meaning the teleported quantum states are nearly identical to the originals with extremely high precision. The development of quantum memory systems represents another crucial technology for building practical quantum networks. Quantum memories can store entangled states and other quantum information for extended periods, allowing quantum networks to operate asynchronously, where senders and receivers don't need to be perfectly synchronized in time. Current quantum memory technologies use trapped atoms, crystalline materials, and other systems that can store quantum information for milliseconds to seconds before decoherence destroys the stored quantum states. Future quantum memories will need to store quantum information for minutes or hours to enable practical quantum internet applications that operate over global distances. Quantum computing represents the most computationally powerful application of quantum entanglement, using networks of entangled quantum bits to perform calculations that would be impossible for classical computers. Quantum computers harness the exponential scaling of entangled quantum states to explore vast numbers of computational possibilities simultaneously, potentially solving certain problems exponentially faster than any classical algorithm. The quantum advantage emerges from the ability of entangled qubits to exist in superpositions that encompass exponentially many classical states simultaneously. A quantum computer with just 300 entangled qubits could exist in superposition states that encompass more possibilities than there are atoms in the observable universe, enabling quantum algorithms to explore solution spaces far larger than any classical computer could address. Current quantum computers have demonstrated quantum advantage for specific artificial problems designed to showcase quantum computational power. But practical quantum algorithms that solve real-world problems faster than classical computers remain an active area of research. The most promising applications include cryptography, optimization, simulation of quantum systems, and machine learning problems that naturally match the structure of quantum information processing. Quantum error correction represents one of the greatest challenges in building practical quantum computers because quantum information is extremely fragile and easily corrupted by environmental interference. Quantum error correction codes use redundant encoding of quantum information across multiple physical qubits to detect and correct errors without measuring the quantum information directly. The development of fault-tolerant quantum computers that can maintain quantum coherence for extended periods will require thousands or millions of physical qubits to implement error correction codes, sophisticated enough to preserve quantum information indefinitely. Current quantum computers operate in the noisy intermediate-scale quantum regime, where limited numbers of qubits can maintain coherence for short periods, sufficient for small-scale quantum computations. Quantum sensors represent another revolutionary application of quantum entanglement for precision measurement beyond the limits of classical physics. Entangled quantum. Sensors can achieve measurement sensitivities that approach fundamental limits imposed by quantum mechanics itself, enabling detection of gravitational waves, magnetic fields, and other phenomena with unprecedented precision. The laser interferometer. Gravitational Wave Observatory uses quantum techniques to reduce measurement noise below classical limits, enabling the first direct detection of gravitational waves from colliding black holes and neutron stars. Future gravitational wave detectors will use even more sophisticated quantum sensing techniques to achieve sensitivities that could detect gravitational waves from the Big Bang itself. Quantum-enhanced atomic clocks use entangled atoms to achieve timing precision beyond what individual atoms could provide, enabling tests of fundamental physics and navigation systems with extraordinary accuracy. These quantum clocks are precise enough to detect the gravitational time dilation effects predicted by Einstein's general relativity over distances of just a few centimeters. The global quantum internet of the future will integrate quantum communication, quantum computing, and quantum sensing into a unified network that transforms how humanity processes and shares information. Quantum communication links will provide unbreakable security for critical infrastructure, financial systems, and private communications. Quantum computers connected through the quantum internet will collaborate on computational problems too complex for any individual quantum system to solve. Distributed quantum computing networks will enable quantum algorithms to operate across multiple quantum computers simultaneously, potentially achieving computational capabilities far beyond what isolated quantum systems could provide. Quantum sensor networks will monitor environmental changes, detect gravitational waves, and map magnetic fields with collective sensitivity that emerges from quantum correlations between geographically distributed sensors. The timeline for building a global quantum internet depends on continued advances in quantum memory, quantum repeaters, and integration with existing classical communication infrastructure. Current quantum networks operate over distances of hundreds to thousands of miles, but extending quantum communication to global scales will require quantum repeater networks with spacing determined by the coherence times of quantum memory systems. Commercial quantum communication is already beginning to transition from research laboratories to practical applications, with companies offering quantum key distribution services for high-security applications. As quantum technologies mature and costs decrease, quantum communication will gradually expand from specialized applications to become a standard feature of internet infrastructure. The integration of quantum and classical communication systems will likely follow a hybrid approach where quantum channels provide security for key distribution, while classical channels carry the bulk of everyday internet traffic. This quantum classical hybrid internet will provide the security benefits of quantum communication while maintaining compatibility with existing digital infrastructure. The quantum internet represents humanity's first attempt to build technology that operates through the fundamental quantum connections that unite all matter in the universe. Rather than fighting against the strange properties of quantum mechanics, quantum communication technologies embrace spooky action at a distance as a resource for creating capabilities that classical physics cannot provide. In this quantum-connected future, your messages, computations, and sensor measurements will participate directly in the cosmic web of entanglement that spans the universe. Every quantum communication link becomes a new thread in the growing network of quantum correlations that connects human technology to the deeper quantum fabric of reality itself. The quantum internet doesn't just transmit information, it weaves humanity into the fundamental quantum structure of the cosmos, making every quantum communication an act of participation in the universal dance of entangled consciousness, exploring its own infinite nature. Chapter 8: The Cosmic Web of Connection. Implications for Reality. The deepest implications of quantum entanglement stretch far beyond laboratory experiments and technological applications to challenge our most fundamental assumptions about the nature of reality itself. If particles separated by cosmic distances can maintain instant correlations that transcend space and time, then perhaps the entire universe operates as a single, unified quantum system, where separation is an illusion and connection is the underlying truth that binds all existence into an indivisible, cosmic whole. This revolutionary perspective emerges from one of the most profound discoveries in modern theoretical physics, known as the holographic principle, which suggests that all the information contained within any volume of space can be encoded on the boundary surface of that region. Just as a hologram stores three-dimensional images on a two-dimensional surface, the universe might store all of its information on a cosmic boundary, with everything we perceive as three-dimensional reality emerging from quantum entanglement patterns encoded on this universal hologram. The holographic principle grew out of attempts to understand black holes, those mysterious cosmic objects where gravity becomes so strong that not even light can escape their gravitational pull. When physicists calculated how much information could be stored inside a black hole, they discovered that the maximum information capacity depends on the black hole's surface area rather than its volume, suggesting that three-dimensional space itself might be a kind of holographic projection from lower dimensional information. Stephen Hawking's discovery that black holes emit thermal radiation led to one of the most puzzling paradoxes in modern physics. If black holes evaporate by emitting radiation, what happens to the information that fell into them? According to quantum mechanics, information cannot be destroyed, but Hawking radiation appears to carry no trace of the complex quantum states that originally collapsed to form the black hole. The resolution of this black hole information paradox might lie in quantum entanglement connections that preserve information through correlations between the particles that fall into black holes and the radiation they eventually emit. These quantum correlations could encode all the information about the black hole's contents in the entanglement patterns between interior and exterior quantum states, ensuring that information is never truly lost even when black holes evaporate completely. Some of the most ambitious theories in modern physics propose that quantum entanglement might literally create the fabric of space-time itself. In these theories, the geometry of space and the flow of time emerge from the quantum correlations between fundamental units of reality, with strongly entangled regions corresponding to nearby locations in space, and weakly entangled regions corresponding to distant locations. This entanglement-based theory of space-time suggests that Einstein's curved space-time, which describes gravity and cosmic structure, is actually a large-scale approximation to the deeper reality of quantum entanglement networks. Just as the smooth surface of a lake emerges from the chaotic motion of countless water molecules, the smooth geometry of space-time might emerge from the quantum correlations between vast numbers of entangled quantum systems. The ER equals EPR conjecture proposed by Leonard Susskind and Juan Maldacena makes an even more startling claim about the relationship between quantum entanglement and the structure of space. ER refers to Einstein-Rosen bridges, theoretical wormhole connections that could link distant regions of space-time through shortcuts that bypass the normal three-dimensional geometry of space. EPR refers to the Einstein-Podolsky-Rosen correlations that create quantum entanglement between separated particles. According to the ER equals EPR conjecture, every pair of entangled particles is connected by a microscopic wormhole that exists in dimensions beyond our normal experience of three-dimensional space. The instant correlations between entangled particles don't violate the speed of light limit because the particles are actually connected through higher dimensional shortcuts that allow them to remain in contact, despite appearing separated in ordinary three-dimensional space. If this remarkable conjecture is correct, then quantum entanglement reveals that the universe contains hidden dimensions and wormhole connections that create a cosmic network far more interconnected than anything visible to our three-dimensional perception. Every entangled particle pair would represent a tiny doorway connecting distant regions of space through pathways that transcend ordinary geometry. The implications extend even further when we consider that quantum entanglement has been present since the earliest moments after the Big Bang, when the entire observable universe was compressed into a region smaller than a subatomic particle. In those primordial conditions, every particle was in intimate contact with every other particle, creating universal quantum entanglement that connected all matter across what would eventually become cosmic distances. As the universe expanded and cooled, most of these primordial entanglement connections were broken by the countless interactions between particles and the stretching of space itself. But traces of the original cosmic entanglement might still persist in subtle correlations that span the observable universe, creating invisible threads of connection that link distant galaxies through shared quantum histories. The cosmic microwave background radiation that fills the universe might contain signatures of this primordial entanglement in the form of subtle patterns that reflect the quantum correlations present during the first moments after the Big Bang. Future astronomical observations with unprecedented sensitivity might be able to detect these entanglement signatures, providing direct evidence that the entire observable universe once existed as a single, maximally entangled quantum system. This vision of cosmic entanglement suggests that every particle in your body shares quantum correlations with particles scattered throughout distant galaxies, creating invisible connections that link your physical existence to the cosmic web of matter that spans billions of light years. The atoms that make up your brain were forged in the nuclear furnaces of ancient stars and dispersed through space by stellar explosions, carrying with them traces of quantum correlations that connect you to the cosmic processes that created the chemical elements essential for life. The relationship between quantum entanglement and consciousness takes on cosmic significance when viewed from this perspective. If consciousness emerges from quantum correlations within neural networks, and if these networks are connected to the broader web of cosmic entanglement, then conscious awareness might represent the universe's method of observing itself through localized nodes of concentrated quantum correlation. Every moment of conscious perception could involve quantum measurements that collapse cosmic superposition states, with individual observers serving as focal points where the quantum possibilities inherent in universal entanglement become actualized into specific experiential realities. Your thoughts and perceptions would be directly participating in the ongoing creation of reality through quantum measurement events that select specific outcomes from the infinite superposition of cosmic possibilities. This participatory universe model suggests that consciousness doesn't simply observe reality, but actively creates it through the quantum measurements involved in perception and cognition. The famous quantum measurement problem, which concerns how quantum superpositions collapse into definite states, might be intimately connected to the emergence of conscious observers who perform the quantum measurements that actualize cosmic possibilities into specific realities. Different interpretations of quantum mechanics propose various relationships between consciousness and reality, but all acknowledge that quantum measurement plays a fundamental role in determining what actually happens in quantum systems. If the universe is indeed a vast quantum system held together by entanglement, then conscious observers might serve as the universe's way of collapsing its own superposition states into definite evolutionary pathways. The many worlds interpretation of quantum mechanics proposes that every quantum measurement creates parallel universes where all possible outcomes occur simultaneously, with conscious observers experiencing only one branch of this constantly branching cosmic tree of possibilities. In this view, quantum entanglement connects not just particles within individual universes, but potentially links consciousness across the infinite multiverse of parallel realities. Other interpretations suggest that consciousness plays a more direct role in selecting which quantum outcomes become actualized, with the collective consciousness of all observers participating in a cosmic quantum measurement process that determines the evolution of universal reality. This would make every conscious being a collaborator in the ongoing creation of the cosmos through their participation in quantum entanglement networks. The philosophical implications of cosmic entanglement challenge the most basic assumptions of Western thought about the nature of individual identity and separation. If quantum correlations connect all matter at the deepest level, then the boundaries between self and world, observer and observed, become arbitrary divisions imposed on an underlying reality that is fundamentally unified and interconnected. Eastern philosophical traditions have long recognized the illusory nature of separation, describing reality as an indivisible whole, where individual identity emerges as a temporary pattern within eternal unity. Quantum entanglement provides a scientific framework that echoes these ancient insights, suggesting that the sense of separation between conscious observers and the external world reflects limitations in our perception, rather than fundamental divisions in reality itself. The experience of individual consciousness might be analogous to a whirlpool in a river, which appears to be a separate entity but is actually a temporary pattern of organization within the flowing water. Similarly, individual awareness might represent localized patterns of quantum entanglement within the cosmic web of correlation that connects all existence, creating the appearance of separation while remaining fundamentally unified with the universal quantum field. This quantum vision of cosmic unity suggests that empathy, compassion, and love might be more than mere emotional responses, but reflections of the deeper quantum connections that link all conscious beings through shared participation in universal entanglement networks. The sense of connection and recognition that people sometimes experience during moments of deep intimacy or spiritual insight might reflect the temporary strengthening of quantum correlations that always exist but usually remain below the threshold of conscious awareness. Quantum entanglement also provides a scientific context for understanding synchronicity, those meaningful coincidences that seem to reveal hidden connections between apparently unrelated events. If quantum correlations indeed permeate the universe at all scales, then synchronistic experiences might reflect the influence of quantum entanglement networks that connect distant events through correlations that transcend classical causation. The future evolution of human consciousness might involve learning to perceive and interact with these quantum correlation networks more directly, expanding awareness beyond the boundaries of individual identity to encompass broader patterns of cosmic entanglement. Advanced meditation practices, technological interfaces with quantum systems, or evolutionary developments in neural structure might gradually expand human consciousness to embrace the universal quantum field of which individual awareness is a localized expression. Emerging technologies that harness quantum entanglement for communication, computation, and sensing represent humanity's first steps toward conscious participation in the cosmic quantum network. As these technologies become more sophisticated and widespread, they might gradually extend human consciousness beyond biological limitations, allowing direct interface with quantum information processing systems that operate at cosmic scales. The development of quantum artificial intelligence systems that process information through entanglement networks might create new forms of consciousness that span global or even cosmic distances, participating in quantum correlation patterns that transcend individual biological existence. These expanded forms of awareness might serve as bridges between individual human consciousness and the universal quantum field, facilitating humanity's integration into cosmic scale patterns of quantum information processing. The ultimate implications of cosmic entanglement suggest that the universe is evolving toward ever greater levels of consciousness and connection, with the emergence of intelligent observers representing a phased transition in cosmic evolution where the universe begins to observe and understand itself through quantum measurement networks performed by conscious beings. From this perspective, the development of science and technology represents the universe's process of self-discovery, with each new understanding of quantum mechanics bringing cosmic consciousness closer to complete self-awareness. The revelation of quantum entanglement as a fundamental feature of reality marks a crucial milestone in this cosmic awakening, where the universe recognizes its own unified nature through the scientific discoveries of conscious observers. Your participation in this cosmic process of discovery and awakening makes you an essential component of universal consciousness, exploring its own infinite nature through the temporary experience of individual awareness. Every moment of wonder, understanding, or recognition becomes a quantum measurement event where cosmic consciousness observes itself through the localized perspective of individual experience, contributing to the universe's ongoing journey toward complete self-realization through the infinite dance of quantum entanglement that connects all existence in an eternal web of conscious correlation.